Okay, in this section 6.5, we're going to find the real roots of polynomial equations. We need to recall the zero product property. The zero product property states that if I set each factor equal to 0, that will solve for x and give un x equals 0. Okay, so we're going to start out with factoring. So the easiest way when you have a trinomial is to find your GCF. So factor out your GCF. And then see if you could factor the trinomial. Set each factor equal to 0. And solve. Okay, in B, we can't factor that unless it says equal to 0. And then I factor this, because this is a 4 and this is a 2, I know it's going to be x squared. And then this further factors because it's a difference of 2 squares. And setting each factor, oops, made an error, sorry about that. Setting each factor equal to 0, you would get x equals -3, 3, -2, and 2. So you should go ahead and try the two check it outs. Set each factor equal to 0, and you should get that result. We learned when we have 4 to try factoring by grouping. So you'll get x equals 5, -5, and 2. Why do you set each factor equal to 0 to find the roots? Roots are where graph crosses x-axis. So y equals 0. And that's for both of these questions. Okay, we're going to continue with this in what's called finding the multiplicity. So what happens is a root can occur more than one time. So in one of our prior examples, we had only 2 roots, but an exponent of 5. So that means that our roots occurred more than one time. Multiplicity is how often a root occurs. We can't always determine that from a graph, but they'll say that if it's a odd multiplicity greater than 1, the graph bends as it crosses the x-axis. If it's an even multiplicity, the graph will just touch the x-axis but not cross it. Okay, and we'll do some sample problems. If you graph A, you'll find that it does have factor of 2. Oh, whoops, that should have been negative 8. Sorry about that. And I have to do synthetic again, and you'll find that it's a 2 again. And you have x squared minus 4x plus 4, which is x minus 2, x minus 2. X equals 2 twice. So you actually end up with 2, the multiplicity of 4. And then with B, when you graph that, you end up with negative 1 as one of the roots. You could also factor out a GCF of x to the third. Oh, I guess I could have factored it out as 2 also. Should have probably done that. Oh well. So we have 2x squared minus 24x plus 72. So I'm going to factor out a 2 here, so that we get x minus 6, x minus 6. So you get x equals 6 twice, a negative 1. And up here you still have x to the third equals 0, which is 0 3 times. So you have 0 with the multiplicity 3, 6 with a multiplicity of 2, and negative 1 with a multiplicity of 1. Okay, I'm going to continue with the day 2, which goes into the rational root theorem. The rational root theorem says that we have, we can find every root imaginable or possible, where P is a factor of the constant term, which is the last term, and Q is a factor of the leading coefficient, and we can write it in the form P over Q. So what that means is it gives you an where you can start, all the possibilities. So the first thing we're going to do is an application. We have this popcorn box, and we're designing a new box, and we want the width 2 inches less than the length, and the height 5 inches greater than the length. And the total volume can only be 24 cubic inches. So I know volume is multiplying all my dimensions together. And I know again that can only equal 24. So multiplying this, and I know I have to subtract the 24, so it's set equal to 0. Okay, so the p-values are all of the factors of my constant. So, and they can all be plus or minus, because you can multiply negative 1 times 24 will give you negative 24, or you can multiply positive 1 times negative 24. 3, 4, 6, 8, 12, and 24. And then Q, leading coefficient is a 1, so it's the only factors. And P over Q, since Q only has 1, P over Q would be all of my possibilities from P. So then you test the possible roots. So I know the length must be positive. And I know I can't start out with 1 because 1 minus 2 is going to give me negative 1. I can't start out with 2 because 2 minus 2 will give me 0. So I'm going to test the first possibility is going to be 3. So I put a 3 and you do synthetic division. So 3 with 1, 3, negative 10, negative 24. And I got lucky right off the bat. And then I factor that. And when I solve those, they are going to give me negative answers. So I know the possibilities for those as a solution can't be. So my answer is then x equals 3. And we already factored in step 3. Okay, so let's try to check it out. So it says we have the width should be 1 foot less than the length. So I'm going to let L be the length. And it says the height should be 4 feet greater. So volume is going to be L times L minus 1, L plus 4, and the total volume can only be 12. And I know I need to subtract that 12 in order to solve. So we find all the possibilities. Again, since Q is 1, I know my P over Q's are going to be the same as my P's, which are my factors of 12. Because I'm subtracting 1 from my variable, I can't be 1. And it can't be negative since we're talking about dimension. So I'm going to try 2 first. Just so happens it works. And this factors into this is x plus, it's not going to factor into 2 nice factors. Oh yeah, 3 and 2, my bad. Wasn't thinking. 2 factors of 6 that add up to 5. And these are going to give you negative numbers. So my answer is L equals 2. And it was asking for the length, and that would be the length. So that works. Okay, well, not every polynomial is going to have rational roots, or roots that can be written as fractions. So we have what's called the irrational root theorem that tells us that if we have an irrational root, it's going to have its pair. They're going to be conjugates. So if it has the square root of 2, it's going to have the negative square root of 2. Okay, so if we have an a plus bc as a root, we're going to have a minus bc as a root. So we're going to use the rational root theorem first to identify all the possibilities. So in this case, my p is plus or minus 1, plus or minus 2, 3, 6. But q this time isn't 1, so I have to do all the factors of 4. And then p over q is going to be all of my p's over 1. And then all of my p's over 2. And then all of my p's over 4. It's nice to graph this to get a starting point, to get an idea. And when you graph it, it does go over 2. Kind of looks like something like that, where this is a nice number. And there is one at negative 0.75. So we test those. So I'll test 2 because that's the easier one. Oh, I got this wrong. Should be and then we have negative 16, 3, 6, 0. And then we'll have to do the other one, which I said was negative 3/4. And you end up with 4x squared minus 16x plus 4. And I can factor out a 4 for that. And we do know that it doesn't matter factors of 1, there's no possibility I can get a negative 4. So you have to do the Pythagorean theorem, which is the opposite of b, plus or minus b squared minus 4 times a times c all over 2 times a. And we simplify that. Square root of 12 simplifies into 2 root 3. So you get 2 plus or minus square root of 3, along with your other roots. So 2, negative 3/4. 2 plus the square root of 3. 2 minus the square root of 3. And we did step 4 with step 3 all on the first page. So you have one problem to try. Doing all of the steps. Doing your P, your Q, P over Q, graphing, synthetic division, can find the rational roots, and then the real roots will include the square root ones, conjugates. Graphing this, you'll find that you have a starting point of negative 1/2. Can factor out a 2, and then your opposite of b plus or minus b squared minus 4ac all over 2a. So you get 2 plus or minus the square root of 20, which is 2 root 5. So you get 2 plus or minus this, 1 plus or minus square root of 5. So all of your answers are negative 1/2, 1 plus the square root of 5, 1 minus the square root of 5. So what are the steps? So the steps are: use the rational root theorem, which is your P over Q, graph, and then test. The last one would be use quadratic formula to find the irrational ones. And this ends 6-5.